So, there's a lot of linear algebra notation here. We went through this last time. It's I'll call it a necessary evil only because if I wanted to make sure that I updated the notes, I had to do it quickly. So I just grabbed whatever I could from my linear algebra notes, popped it in here, and then tried to edit it as best as I could. And I guarantee something fell through the cracks here, but that's your gain if you get typo bonus for that. All right, it's objective to learn how to use matrices plural of matrix, to perform transformations in the vector space. All right, so we're talking about real space dimension n transforming to real space dimension m, in that they're not going to necessarily have the same dimensions after the transformation, which is a really cool thing to think about, because depending on the transformation, you might end up going from 2 dimensions to 3 dimensions back to 1 dimension. There's a lot of different possibilities. All right. There exists a unique matrix A such that, and this is what we call a matrix equation, T of x is equal to AX, where A is it's not a constant multiple or anything like that. It's actually a matrix. All right. So this is the product of the matrix and a vector for all x in that particular real space. All right. So that funky looking R is the best I could come up with for, in Microsoft Word for real space notation, which is actually supposed to be, like the set of real numbers, but I couldn't find the notation for that. And I'm not savvy enough with programming to make it work. So in R2, we tend to say that T of xy is equal to the product of A and vector xy, which can also, for convenience, be written as, and I say convenience loosely here, because we use, in this course, we've used this vector notation, but in linear algebra, we use this vector notation. So instead of writing it as a row vector, we'll write it as a column vector to facilitate the act of matrix multiplication. It makes it a little easier to go through that process. Right. There's schools of thought either way, but most people kind of adhere to this convention. Right. A is the known standard matrix for the linear transformation. It's usually given to you, or it's something that you can easily determine based off of whatever it is you're trying to do. And I'll show you what that means in a couple minutes. Right. It's an M by N matrix. Right. So it doesn't necessarily have to have the same dimensions horizontally and vertically. Whose jth column. Right. Jth column is the vector. We call it, just to make things as complicated as possible, T of E sub J, where E sub J is the jth vector of the identity matrix in our real space M. Alternatively, the notation starts getting out of hand. Again, because this is something that's kind of a later Unit 1 topic in linear algebra. So we would have built towards understanding this notation, and here I'm kind of throwing it at you all in one shot. It's not really fair for me to expect that you'll just understand what this is talking about. But basically what this is telling us is that you're going to have a matrix A. That matrix A is going to be comprised of what are called transformation vectors. Each one of those vectors contributes to the overall transformation from one system to another. Depending on the dimensions of the transformation matrix, when you multiply that by whatever the vector is you're working with, it could be a simple numerical vector, or it could be a vector value function. It'll serve to transform that into whatever it's going to transform it into, depending on what the goal of the transformation is. All right, that's all that notation means. It's the act of multiplying your transformation matrix A by the known vector, whatever it is. All right. So for number 1, it says find the standard matrix A for the dilation transformation, T of X is equal to 4X for X in R2. All right, so I'm just going to draw a quick sketch here. It's not, these sketches aren't going to be as complicated as what we did on the previous page, but it's really the idea that if you have some sort of vector in space, two-dimensional space, because it says in R2, we're working with assuming the XY coordinate plane. Okay. It doesn't necessarily have to be the XY coordinate plane, but it kind of is implied here, especially since it says XY here. But just so you know, whenever they say X in the form of a vector, it's dependent on the number of dimensions. So that X is really equal to the column vector X of 1, X of 2. Okay, so it's an unknown first dimensional and second dimensional component comprised together, or two unknown components comprised or composed together or put together, whatever, to give you a vector in two-dimensional space. So that usually is interpreted as, all right, this is our X value and this is our Y value. All right. So, you know, just to kind of put it in terms that we're all familiar with. So let's say, for example, that we're just working with the unit vectors in R2. All right. So I'm just working with I. And we'll call that U. And we're working with J. Okay. What this is telling us is that we're going to take these vectors. It's a dilation transformation. That's a scalar multiple. It's telling us that we're going to quadruple these. So whatever the length is of each one of these, I'm going to tack it on 3 more times in order to quadruple it. So 1, copy, 2, and this. A little X is in the way and it's messing me up. And 3. Now let me get this X out of the way. All the X's are in the way. Crazy. Okay, so that gives us 4I. And we would do the same thing with J. All right, figure out what its length is. So 1, 2, 3. So it's now quadruple its original length. Now it's not perfect, but you get the idea. And this would happen with every vector that's in this two-dimensional space. So if I had something just kind of going off into the first quadrant somewhere, you know, like vector 1, 2, I would be quadrupling each piece. Right? So that's what's happening there. It's just a question of, okay, well, what does that mean? Well, I is the vector 1, 0. 4I is the vector 4, 0. J is the vector 0, 1. For J is the vector 0, 4. All right. So what's happening here is we're starting off with a matrix that's composed of I and J. I go back and forth with composed and comprised. I'm pretty sure I'm using both of them wrong, but you get the idea. Put together. All right. And I also say you get the idea, hoping that you actually do get it. All right. So this is a matrix. This is where we're starting. 0. I'm sorry. 1, 0, 0, 1. The I vector 1, 0, the J vector 0, 1. It's becoming after we quadruple it, 4i, 4j. Right? So, so that's 4004. That 4004 is the standard matrix A for the dilation transformation, right? Because what we could actually do is factor out a 4 here, a scalar factor from the entire matrix. And when you factor out a number, you're dividing each entry by that matrix, or of that matrix by that number. So it would be 4 times 1001. And so we're looking at this as saying, well, that's the only difference between what we call the identity matrix in the XY plane, 1001. That's the matrix that defines the XY coordinate system, because its two components are 1001, as in the I and J vectors. It's becoming 4 times that. So whether you multiply each component by 4, you multiply the whole matrix by 4, and then just multiply it through, either way, this now becomes the matrix that defines the new system, right? So what I would say here is, just going back to what I was talking about before, let's say you had the vector 1, 2. And so 1, 2 would be right here, roughly, based off of this sketch. All right, so I'm going to write it in the column vector form, 1, 2. If we wanted to figure out what that would be in this new coordinate system, all we would have to do is multiply that by the basis of the new coordinate system, which is 4004. So I could do that using my, and they didn't ask for that in this problem, just using it to demonstrate. So I'll use my matrix calculator. I'm going to take first my matrix A. So new matrix 2 by 2, 4004. 0, right arrow, 0, right arrow, 4. Then I'll put in this new matrix, but it's a 2 by 1. So let me get rid of a column, having components 1, 2. All right, and so all I would be doing is multiplying matrix A by matrix B, and you see it becomes 4, 8, which is what you would get if you multiplied each piece, each component of that 1, 2 vector by 4. All right, so the multiplication of the standard matrix for dilation transformation got the job done. All right, so this is really what our answer is, but then it begs the question, either one of these actually, but I'll just box this one. It's a little bit more concise, right? But it begs the question of, okay, well, what if it's not so easy? You really have a lot of different ways that you can look at this, but it's kind of cool when you think about the applications. So let me actually show you really quickly. Not too quick, but really super quick. Oh, I need my pen to help me mark it off. All right, so I'm gonna reproduce this. Oh, no. I'm gonna reproduce it over here so I don't lose it. I'm gonna pop that in up there. I'll bring it back in a minute. I'm gonna clean this up. I'm just going to kind of plot a point up here as a little benchmark. I'm going to do the same thing over here. I'm going to get rid of, oh, hang on to this, but I'm going to get rid of all of this. All right. So this is our transformed plane. So this would be x prime, y prime. And so it's a new plane. In this new plane, we've redefined reality so that I is now considered 4, 0. J is now considered 0, 4. What we would be doing based off of this new reality is identifying what this would be in that new reality, what this would correspond to in that new reality, right? So if you transform the whole coordinate system, what's going to happen is that 1, 2, 1 corresponds to a 1i, the 2 corresponds to a 2j, based off of our new i's and our new j's. So what I would have to do is now modify this vector to fit that new scheme. So it's going to grow and grow and grow until it achieves that objective. So it's going to be twice as tall as the j vector, and it's going to be the same length as the I vector, right? Looks pretty terrible like that. So I'm not going to leave it in that form, but that's the idea, right? So you'd have a point that's somewhere up in this neighborhood, and this would be the vector 1, 2 in this new space. All right, what it corresponds to in the xy plane is the coordinates 4, 8. Right, so then what we would do, so this is our transformed plane, is we would actually take this vector, bring it back over here. Now that we've transformed the space to figure out what the length of that vector ought to be, we would bring it back into the regular universe or regular reality so that we could figure out what that would be in the context of that regular reality. All right. Now scale wise is a little bit off, but that's the gist of it. It'd be something more like this. All right. And so for that, we would end up with 4, 8. But all of that stuff, all of that geometric, the behind the scenes calculations and diagramming, that's all happening in the process of the matrix multiplication. That's actually what matrix multiplication is doing for us. So it's a journey into a transformed reality and back. That's what the matrix multiplication does for us. All right. So most people are like, okay, yeah, so it's 4004. You just multiply the 1001 by 4, huh? Good. All right, got it. That's fine, but if you work to try to understand the deeper meaning behind it, it opens a lot of pathways for you. All right. Number 2, it's still a 2 to 2, so 2-dimensional transformation that rotates each point in R2 about the origin through an angle of phi with counterclockwise rotation for a positive angle. Find the standard matrix of this transformation. Right. So a rotation around an XY plane. It sounds like a movement around a circle, because it is. So if I draw XY plane. I did that before, and that's what I get. So let me try to make it at least look a little circular before I let it autocorrect. If I'm starting off with the IJ unit vectors, so in the direction of 0 degrees or 0 radians, I have I, but that corresponds to the unit vector 1, 0, or J, which also corresponds to the unit vector, but for a unit vector, but this time 0, 1. I want to make a counterclockwise movement. All right, so if I take this right angle and rotate it in a counterclockwise fashion, I'm going to get a new right angle, depending on what that angular movement is. So let's say I move it somewhere in the neighborhood of 30 degrees. All right, that's going to be my phi. All right, so I got this new vector, still magnitude of 1. That's all good, but it's defined based off of cosine comma sine. Okay, so because every coordinate around this circle that has a radius of 1 is defined by cosine comma sine. But as I moves, so does J. All right, by the same angular movement. All right, so we got another phi over here. All right, so it really just kind of begs the question, all right, well, if we're in the unit circle, where do we start and where are we going? Well, in the XY plane, so XY, we're starting off with cosine of 0, sine of 0. That's I. All right, cosine of 0 is 1, sine of 0 is 0. For the J, we're starting off with cosine of 90, or cosine of, I'll say pi over 2, sine of pi over 2. That corresponds to 1, 0, 0, 1. All right, so that's our standard. It's really a transformation matrix where every XY vector in dimension 2 transforms to itself, right? Which is why we call it an identity matrix. Right? When you multiply it by any vector, the vector remains unchanged. Right? So what's going to happen is my angles are going to increase by some value phi. So in my x prime, y prime plane, so my transformed plane, we're going to have cosine of 0 plus phi, sine of 0 plus phi, cosine of pi over 2 plus phi, sine of pi over 2 plus phi. And depending on what phi is, we'll get our rotation. For a positive, a counterclockwise gives a positive angle, so we're good there. It didn't say anything about additional restrictions, like it had to be acute or anything like that, so we're in pretty good shape. All right, so if, for example, I wanted phi to be equal to pi over 6, then I would get a transformation that would get me to radical 3 over 2 comma 1/2, or radical 3 over 2 1/2 vector, and then negative 1/2 radical 3 over 2 for the other column vector. All right, but that's all dependent on whatever the value of phi is. All right, but that would be the matrix that you would multiply any vector by in order to create that transformation. All right, so what does that mean? And it's always, what does that mean? Well, it was kind of easier when we talked about a dilation matrix to conceptualize it, because we're redefining the IJ coordinate system based off of, you know, XY being IJ as unit vectors being 1, 0, 0, 1. they became 4, 0, 0, 4, but we're still treating those as unit vectors just in a new reality. What this is basically saying is whatever we call phi is now going to be defined as a horizontal line in that new reality, right? So what I would be looking at is, and I'll take this copy. I would get rid of all this stuff. This would be my x-axis. I'm just trying to make it match up somewhat. And this would be my y-axis. All right, so this is x prime, y prime. And so if I had one unit in the x direction, I would now be defining the I value as whatever this is, whatever this vector is. In this case, I'll stick with the other notation. Cosine of phi, sine of phi. And J here cosine of phi plus, the whole thing. Right? So cosine of phi plus, I'll actually just move it over, 90 or 90 plus phi. Or in this case, pi over 2, because I went radians. Sine of pi over 2 plus phi. All right, but then, so that would be how we would define a unit vector. But we'd have the added bonus of saying, all right, well, once I figure out what that is, I would then transport it back to the XY plane and go from there. Yeah, so everything would now be measured in terms of I and J having this dimensional relationship. So if I said I had a coordinate or a vector, sorry, 3i plus 4j, I'd be going to 3, 2, 3, 4, somewhere up in this neighborhood. That would be the vector, which would then get transported back to the XY plane in order to see where that would be in terms of a fit for that coordinate axis. All right. So then what ends up being the case is once you establish that everything is in terms of XY, I's and J's in this coordinate system, we actually go a step further and say, well, I don't want to have to make a graph that looks like this, but I still, maybe I want to live in this coordinate system, right? But I don't want to have to, instead of saying I want to make a left turn or a right turn when I'm driving down the road, I have to say, well, I want to make a 230-degree. I don't like that. So what we would do is we would actually take the I and J values and plot them on a horizontal and vertical axis. So every one of the tick marks on this axis that I would call I, that would actually have a unit vector of one space, would correspond to this I. So we could actually think of it in linear terms, but still visualize it or at least have an analogous relationship in the rotated reality. All right. So this is just a rectangular way of representing these coordinates. Very interesting and also mind-bending at the same time. All right. At the bottom of the page here, you have just a refresher on different rules for geometric transformations. You know, it's old high school stuff. You know, you did this plenty of times, but it's very easy to forget some of it, especially the rotation one, right? But that being said, that 90-degree rotation is just a specific case of what we were just talking about. Right? So it's not something you really need to worry about, the rotations, because we just kind of tackled that. Right? So let me take you through the process for actually transforming a coordinate. Find the image of vector 2, 3 under the transformation of x negative y, and then draw the coordinates and describe what you observe. So if I have vector 2, 3 in the xy coordinate plane, I'm going to write it like this, 2, 3. The transformation is x negative y. All right, so x stays put, y gets negated. All right, so what we do, since we know we're starting off with the standard, that should be a 1, 1, 0, 0, 1, the standard identity matrix, we take I, which is equal to 1, 0, and j, which is equal to 1, 0, 1. I don't know what. And perform the transformations on those, right? So it's basically like, okay, so if I'm going to leave any x components alone, what does that mean for I? It means I is going to stay put, right? I is not changing. If I'm going to negate any y values, what does that mean? That means that the j value, instead of being a positive j, is going to be a negative j. All right, so negative j would go down here, and you'd have j is equal to 0, negative 1. So I'm basically saying that take your identity matrix and transform it column by column based on what's happening to the I and j vectors. So I stayed put, so that's going to be a 1, 0. J got flipped over the x-axis, so that's going to be 0, negative 1. All right, so this is our standard transformation matrix A. If I want to actually transform, so draw the vectors, we did that. We need to actually transform 2, 3 to see where it's going to end up. Now that's a reflection over the the y-axis. So we know it's going to be 2, negative 3, but let's verify it to make sure. So I would be taking A and multiplying it by the 2, 3 vectors. So that would be 1, 0, 0, negative 1 multiplied by 2, 3. All right, you could do it using the dot product approach, or you could just do it in Desmos. All right, so sometimes it's easier to do it by hand because it takes longer to type it in. 0, sorry. But then once you do it on Desmos, it's like, all right, it's not that bad. You get the hang of it, it's not too bad. So 2, negative 3, that checks out. So instead of going up 3 units, we're going down 3 units. And so that's our transformed vector. All right, so that's 2, negative 3. All right, and so that's a reflection over the y-axis. All right. The rotation stuff, we talked about that on the previous page. This is really just kind of formally addressing that and actually carrying out the process. If we wanted to find the image of the vector 2, 2 under the transformation, so again, up a quick plot. being the second word of the day. So here's 2, 2. If I'm going to rotate this 90 degrees, I'd want to be thinking about what that means for I and J. So I is here again, J is here.
Sorry, what was that? Quick?
Quick.
I couldn't. Quick?
Yes.
Okay, thank you. Sorry.
No problem. All right, so we're rotating this one, the theta value that's positive 90, well, positive 90 degrees, positive pi over 2. I eventually got there. So what's going to happen is I is going to move to where J is, and J is going to move to where negative I would be. All right, so we're starting off with the standard vector, standard matrix, identity matrix. The 1, 0 is going to where J is. So the I is going to where J is. So that's 0, 1. The J is going to where negative I would be, which is negative 1, 0. Right? It's pretty clean because it's a 90-degree movement from our unit vector. So all I would have to do is multiply the 0, 1, negative 1, 0 by 2, 2. All right. So 0, 1 0, negative 1, I should say. 1, 0. And then 2, 2. And then the product of A and B. Again, just so you don't have to worry about doing that by hand. All right, so 0, 0, yeah, 0, 1, negative 1, 0. Okay, so negative 2, 2. Oh, almost made it a fraction for some reason. All right, so negative 2, 2 would be about right here. And so you take a look and you say, okay, well, what does that look like? It does look like a 90-degree rotation, so we're feeling pretty good about this. All right, so it's a 90-degree counterclockwise rotation. All right. Now, you have what's known as a shear, right? Or any kind of expansion or compression in one direction that's not in the same direction, or doesn't have the same characteristic in the other direction. So the example here, find the image of 2, 3 under the transformation 0.5x comma y. All right, so draw the vector blah blah blah. All right, so 2, 3. Here's 2, 3. We look at our unit vectors in the direction of x, so the I, and in the direction of y, so the j, and we look at our relationship here. This relationship tells me, so we got a 0.5x versus a y. It tells me that the y is staying put. So this one's not changing. But the x is going to be half of itself. All right? So whatever x is, chop it in half, that's what my new x is going to be. That's what my transformed x is going to be. All right? So that's telling me that this little sliver of business right here, which is 1/2 I, that's going to be my new vector. That's going to be my transformed vector. So 1, 0, I keep wanting to put a 0 first. I don't know what. It's crazy. 1, 0, 0, 1 is going to become 1/2, 0, 0, 1. All right. The j vector stays put, but the I vector is the one that gets chopped in half. Half of 0 is still 0. All right. So then we transform 2, 3 by carrying out that multiplication. And just so I can do it at least one time today, I'll do this one by hand. So we're going to take the dot product of the first row and the vector. So it's the dot product of, it's really kind of crazy how we do this, but we're going to think of this as now a row vector dotted against a column vector that's written in row form. That'll be our first entry of our solution vector. And then the dot product of our second row, 0, 1, against the 2, 3. So you're looking at 1 plus 0, 0 plus 3 would result in, well, really, just write it as 1, 3. So using a matrix approach, we're able to come up with, and again, you could have done it on decimals. I just wanted to actually show it the one time. 1, 3 would be our transformed vector. So that would be this location. All right. And that's based off of this rule. X stays put, Y stays put, X gets chopped in half. All right. So we worked with a little bit of, or a few cases where we have some functions or transformations of functions. Here we're working with transformations of constants. We're going to have to be able to handle both. So this is all necessary stuff, right? Which is going to lead us into the concept of the Jacobian. This next page is kind of like beating it all to death a little bit. So we'll skip this. The shear in the X direction is kind of the same idea as what we were just talking about. It's just talking about a transformation in one direction, you know, more pronounced transformation. I mean, we can talk about it next time, so I'll put a star on it. But the 1-to-1 and onto, we're not going to really go too crazy with that. But I will talk about that next time as well, which is going to get us into the concept of the Jacobian determinants, which is where we start bringing the partial derivatives back into the play or into the mix and then going from there. All right, so I'm going to stop the recording and talk a little bit about the tech assignment. Nothing too crazy.